Every light you see, every signal transmitted, every transaction processed in the time it takes you to blink, all of it depends on something you've probably never looked at closely. Something smaller than your thumbnail, lighter than a paperclip, and yet more complex than anything else our civilization has ever built. This is a computer chip, and the story of how it's made begins not in a laboratory, but on a beach. Silicon. The primary ingredient in every computer chip is one of the most abundant elements on Earth. It's found in quartz, in rock, and yes, in ordinary sand. But raw silicon is nowhere near pure enough for a chip. It has to be refined to a standard that seems almost impossible, less than 1 foreign atom per 1 billion silicon atoms. To achieve this, silicon is melted in enormous furnaces at over 1,400 degrees Celsius. Carbon reacts with the impurities and carries them away, leaving behind a material purer than almost anything found in nature. This hyper-pure silicon is then melted again. A small seed crystal is dipped into the surface, and as it's slowly rotated and drawn upward, the silicon solidifies around it, forming a single, perfect crystal, a cylinder about a meter long and over 300 millimeters wide. This process is called the Czochralski method, and it was first developed in 1916 by a Polish scientist who accidentally dipped his pen into molten tin instead of ink. Every atom in this ingot is arranged in a precise, repeating lattice, a structure that gives silicon its unique ability to conduct or block electricity depending on the conditions. The ingot is then sliced into wafers, circular discs that look something like oversized CDs. Each one is only about a millimeter thick. They're polished until the surface is smoother than a mirror, accurate to within a few atoms. Each wafer will eventually carry hundreds of individual chips. But right now, it's a blank canvas. Before any circuit can be drawn onto that wafer, it must enter one of the most tightly controlled environments ever built by human hands. This is the clean room. Keep watching to hear more about the birth of a chip, and don't forget to like and subscribe to get the next upcoming tech video. Okay, let's talk about the clean room. Standard office air contains millions of airborne particles per cubic foot. A hospital operating room reduces that to a few hundred. The clean rooms inside a chip factory? Fewer than one. The air is constantly filtered and recirculated. It flows downward in smooth, parallel streams. Laminar flow, designed to sweep any contaminant away from the wafers before it can settle. A single human hair falling onto a wafer would be catastrophic, like dropping a fallen tree trunk across a city highway. Even a particle invisible to the naked eye can bridge 2 circuits, short them out, and destroy the chip entirely. For this reason, most of the actual handling is done by robots. Human hands are kept as far from the wafers as possible. The first step in building a circuit is coating the wafer in a chemical called photoresist, a light-sensitive material, not unlike the film in an old camera. Then comes the step that defines the entire chip industry: lithography. The machines used for this process are among the most sophisticated ever built. A single extreme ultraviolet lithography machine, made by just one company in the world, in the Netherlands, costs over $150 million and contains more than 100,000 individual parts. Inside, a laser fires at a tiny droplet of tin, 50,000 times per second. Collision produces extreme ultraviolet light, a wavelength so short it can only travel in a vacuum. That light is then focused and reflected through a series of near-perfect mirrors, down through the mask and onto the wafer. The mask is essentially a stencil, carrying the blueprint of one layer of the chip's circuit. Wherever the light passes through, it chemically alters the photoresist below. The exposed areas are then dissolved away, leaving the circuit pattern printed directly on the silicon surface at a scale measured in nanometers, billionths of a meter. For context, the transistors on a cutting-edge chip today are roughly 2 to 3 nanometers across. A strand of human DNA is about 2.5 nanometers wide. We are, quite literally, working at the boundary of the molecular world. And this isn't done just once. The process is repeated dozens of times, each pass adding another layer of the circuit, stacked with atomic precision. Like printing a skyscraper, one floor at a time, from the air. After each layer is exposed, the unwanted silicon or material must be removed, a process called etching. Plasma etching uses electrically charged gas to carve the surface with extraordinary precision, removing material at the scale of individual atomic layers. Chemical etching uses reactive fluids to achieve similar results in different contexts. What's left behind is the exact three-dimensional structure the engineers designed. Next comes one of the most counterintuitive steps in the entire process, deliberately contaminating the silicon. It's called doping. By firing atoms of elements like phosphorus or boron into the silicon at high velocity, engineers can alter the electrical behavior of specific regions. Some zones become rich in free electrons. Others develop an absence of electrons, called holes. This is how transistors are born. Where N-type and P-type silicon meet, a gate can be formed. Apply the right voltage and current flows. Remove it, and current stops. On, off, 1, 0. Repeat that operation billions of times per second across billions of transistors, and you have a machine that can run any computation, any game, any calculation, any conversation. A chip full of individual transistors is like a city full of buildings with no roads between them. To be useful, everything must be connected. This is done through metallization, laying down ultra-thin wires, most commonly made of copper, that link transistors into circuits. The excess metal is polished away using a process called chemical-mechanical planarization, which combines abrasive slurry and physical pressure to achieve a perfectly flat surface. Then another layer of insulation is applied, and the wiring process repeats, higher and higher, layer upon layer. A modern chip can have more than 100 of these metal layers, forming a three-dimensional interconnect network so dense and intricate that no single human mind could design it manually. These layouts are designed by specialized software, guided by engineers, and verified by simulation before a single wafer is ever made. By the time metallization is complete, the chip's surface looks completely plain. Everything that matters is hidden within. After months of processing, every chip on the wafer must be tested. Automated probers lower microscopic electrical contacts onto each chip's surface, running thousands of diagnostic tests in seconds. Voltage is applied. Current is measured. Timing is checked. Any chip that fails is marked with a small ink dot. On a good wafer, the vast majority pass. On a bad one, perhaps due to a contamination event earlier in the process, many do not. Yield, as it's called, is one of the most critical metrics in chip manufacturing. A few percentage points can mean the difference between profit and loss. The wafer is then diced, cut apart by a precision saw or laser, separating each chip, now called a die, from its neighbors. The surviving dies are picked up individually and mounted onto a package, a small platform that connects the chip to the outside world. Fine gold or copper wires, thinner than a human hair, are bonded from the chip's surface to the package's contacts. The assembly is sealed with a heat-spreading lid, protecting the silicon beneath. What we now have is the familiar rectangular component, the chip as most people know it. After one final round of testing inside the package, the chips are shipped to device manufacturers across the world who will solder them onto circuit boards inside the products we use every day. From start to finish, making a single batch of chips takes anywhere from 3 to 6 months. It involves over 1,000 individual process steps. It requires machines so precise they must be isolated from vibrations caused by people walking nearby. And it's a global effort. The silicon might come from Norway, the machines from the Netherlands, raw chemicals from Japan, the design from California, manufacturing from Taiwan or South Korea. All of that for something you can barely see. But that small thing powers the world's hospitals, its financial systems, its communications, its science. Every modern convenience we take for granted traces back to the same place. A grain of sand, transformed by ingenuity, precision, and an almost irrational level of human ambition into something that thinks. Hope you found this interesting about the birth of the computer chip. Drop a comment and let me know what other topics you would like to learn about for future videos.